Thanks, Richard. Okay, yeah, so what I want to talk today about is some of the work we're doing, really looking at perhaps where the new clinical markers may come from. Okay, so of course we've heard about the clinical lipid measures today and association with risk. It's very well established, but although we're still learning more. But of course what we need to remember is that these measures of cholesterol and triglycerides are derived from lipoprotein particles. And within these particles, the composition of lipids, so the cholesterol esters and triglycerides are essentially on the hydrophobic interior of the particles, but on the exterior of these particles is many hundreds of different lipid species. These include phospholipids, and they make up the bulk of the exterior, but there's a whole range of sphingolipids that also are present within or on the surface of these lipoprotein particles. And then there's a range of other lipids that might be oxidized or glycated and so on. And the list literally goes on and on. Overall, probably 10,000 or more individual lipid species present in humans. Probably 1,000 of these are present in plasma, at least at levels that we're able to access relatively easily with current technology. The technology that we do use, and I'm not going to dwell on this, but essentially we use liquid chromatography coupled with tandem mass spectrometry. These are the couple of platforms we have at Baker. What that gives you is a chromatogram, or a series of chromatograms, that each of these chromatographic peaks represents an individual lipid species, and here we've got about 500 lipid species measured in around 15 minutes. So that's sort of where the technology is at the moment, and that's just using different chromatography. So these 500 lipid species exist in maybe 20 or 30 individual lipid classes, and you can see some lipid classes have only a single lipid species, some have maybe 100 or 200 lipid species, and again, they break down into a number of subclasses. So again, it gets fairly complicated fairly quickly. And of course, it doesn't end there. While we recognise that lipid species exist within these lipid classes, so the lipid classes exist within metabolic pathways. So they all interact through these fairly complex metabolic pathways. And the reason I'm putting this up is really just to remind us that these are not individual entities. They're part of this metabolic network. And if we're going to understand the results that we see from lipidomic studies, then we need to consider that they do exist in these networks. And so here is just a representation of the area of this network that we're able to cover with our current profiling. Okay, but let's move on to talk about how we use that technology. And the study I want to talk to you today about is the long-term intervention of pravastatin, or with pravastatin, on ischemic disease. So this is the lipid study conducted by John Symes and colleagues in Sydney. So it was a double-blind placebo-controlled study. Everyone had a history of acute MI or unstable angina, cholesterol 4 to 7. They were randomised to placebo or pravastatin. The outcomes that we're actually looking at least, were all cardiovascular events over 5 years, so MI, stroke and CVD death, or we also look at CVD death on its own. And the sample, we didn't have the full sample set, which was 9,000, but we had about 5,000 or just under 5,000 where we had a baseline sample as well as a 1-year follow-up sample. Then we had another 1,000 of baseline only and about 800 of follow-up. And so within this cohort, we had about 700 cardiovascular deaths over the 5-year follow-up period, 650 MI and just over 300 strokes. So we had a lot of power to start to tease out or how lipids were associated with those outcomes. And so we know then that our ability to stratify risk in secondary prevention is limited, and that statins are really a treatment paradigm but may not benefit all patients, or at least not all patients equally. So we had a number of specific questions that we wanted to ask here. Specifically, could lipid species improve the prediction of cardiovascular outcomes? And that's independently of all the existing risk factors that we have. We were interested in what the effect of statins are on the lipid profile and how that relates to future events. And can these lipids predict who would respond well or less well to a statin treatment? Now, today, in fact, I'll just deal with those first two questions. Okay, now, for the lipid study and most clinical trials, fortunately, we have a very large list of baseline characteristics, and you can see that a number of these are associated with cardiovascular outcomes. And so these are all of the characteristics that we subsequently use as covariates in our analysis, because we're looking for lipid species that are independent of all these existing risk factors. So with that background, then we performed our lipid extraction. We used just 10 microliters of plasma. We ran it through the mass spectrometer. We had just under 12,000 samples in this. We were measuring around 350 lipids. So we generate this very large database over several months of mass spectrometry time. And then we asked, can these plasma lipids improve prediction of cardiovascular events? And of course, at the same time, as I mentioned earlier, we're looking to try and understand how these lipids relate to the biology of cardiovascular disease. Okay, so the first study we do then is look for association of lipid species with our cardiovascular outcomes. Again, these are the outcomes we're studying. We're using Cox regression, adjusting for that long list of covariates that I showed earlier. And so we calculate hazard ratios and we correct for multiple comparisons. Okay, now I can't show you 350 lipid species. So this is looking just at the lipid classes that we were studying. And we're looking at which lipid classes then are associated with cardiovascular death. So this is a bit unimpressive. There are two lipid classes that are showing this, not particularly significant association with cardiovascular death. But of course, what happens is, within each of these classes, there are multiple lipid species. And so when we start to dig down then into the individual species within each class, we start to see a large number of species, 55 associated with all cardiovascular events and 95 associated with cardiovascular death. And when we look at what they are and how they behave within the class, we start to understand why we're not seeing this effect at the class level. So here we have three classes of sphingolipids, so dihydroceramides, ceramides, and monohexacylceramide. There are 6 species within each class, and you can see that within each class there are just 2 species that show a significant association with cardiovascular death in this case. And so what we start to see when we look back at our metabolic pathway, here's the pathway that produces dihydroceramide, ceramide, and then subsequently the glycosylated forms. In all of these lipid classes, we'd see the same effect, that these 2 lipid species containing either a 16-0 or an 18-0 fatty acid were positively associated with future cardiovascular death. Now, we also know that the production of these dihydroceramides and ceramides is through a series of ceramide synthase enzymes, and these ceramide synthase enzymes show specificity for the different fatty acids. So what we're starting to see here is that there's likely a level of regulation occurring with this ceramide synthase enzymes that are changing the production of at least the 16 and 18, and that's possibly the synthase 1 and the 5 and 6, that is involved in risk of cardiovascular events. Okay, so that's really trying to understand a bit of biology, but of course we want to assess whether lipids can predict these outcomes. Of course, we don't want to use or create a multivariate model that contains 350 lipids. We want the model with the fewest lipids that gives us the greatest power to predict future events. So we go through a fairly convoluted process of firstly minimizing the number of lipids based on their correlation. We create base models with all of our covariates because we want lipids that are improving on all of the traditional risk factors. We add these lipids sequentially to our base model, and we use this Akiaki information criteria to select those lipids. And then we get a ranking of the top 20 lipids, and then we come back and create a new series of models and use these models to determine C statistics and the net reclassification index. And so we can assess how the performance of the lipids on top of these traditional risk factors. And so this is the type of results we get. So we're looking at the C statistic on the y-axis, and for each model, as we increase the number of lipids, and so you can see we get an increase in the C statistic, it starts to level off around 8 or 10 lipids, and we see cardiovascular events and death. Okay, so to put numbers on that, looking at cardiovascular events, when we add 8 lipids to our base model, we've got about a 2% increase in the C statistic, about an 8% categorical NRI, and about 30% continuous NRI. Slightly better if we're looking at cardiovascular death as the outcome, 4%, 10% and 40% or so. So we can see that lipids are able to improve on our traditional risk factors. These are the lipids that end up in those two models, and they probably don't mean a lot, but there are ceramides here, there are phosphatidyl and inositol species, and we'll come back to those in a moment. Okay, so this is really just a summary of what I was saying. So these lipids are independent of the traditional risk factors. They're giving us some biological insight, I think, into the association with risk at least. They can improve on the traditional risk factors. And I don't have time to go into it now, but we've also validated these lipids in a completely separate cohort, but I won't follow that up now. The second bit I just wanted to touch on was what's the effect of statins on the plasma lipid profile, and then how this relates to risk of future events. Okay, so one way to look at that is to, again, looking at our lipid classes and do the regression analysis to look at the association of statins with or the association of lipids with statin treatment. And what we can see here is, here's our cholesterol and cholesterol esters, which are a representation of LDL and HDL cholesterol. And they're showing this negative association, as you would expect, but so do pretty much all of the other lipid classes that we're looking at, and in fact some of them are really quite strong, or even stronger than the cholesterol lowering that we're observing. But of course what we really want to understand is not the fact that all of the lipids are decreasing along with the cholesterol. We want to understand how the lipids are changing in their relative proportions to cholesterol as we decrease cholesterol. So we can do that by actually adding in the change of the clinical lipids into our model, and now we see again, so now we've effectively adjusted out the effect on cholesterol and cholesterol esters, and in fact most of the other lipid classes. Although we see some of these sphingolipids still showing this negative association even after we've adjusted for the change in LDL cholesterol and total cholesterol. Of course, again, the detail lies in when you look at individual lipid species, and this is the same analysis. Now we're looking at the top 20 lipid species that are significantly associated with statin treatment after adjustment for clinical lipids. What we can see is that there's a number that show a positive association, so I guess the interpretation is that the reduction in these lipids is not as great as the reduction in LDL cholesterol after adjustment for those covariates. And what you can notice here is almost without exception, these are containing arachidonic acid, which is a precursor to eicosanoids and other pro-inflammatory mediators. We also see the negative association, some again quite strong with these species of phosphatidyl and inositol, and again I'll come back to that. Okay, so the question that we're interested in then is, can the change in the plasma lipid species explain the treatment effect of statins? And the way we do that is, again, firstly to create a base model with all of our covariates. We get a relative risk reduction from statin treatment of about 20%. When we adjust for the change in LDL cholesterol in this model, our relative risk reduction is reduced to 9%. So LDL cholesterol is explaining about half of the treatment effect of statins. We then go through a process of individually adding in each of these lipid species. We add in the baseline lipid and the change in the lipid as well as an interaction term, and look at what the relative risk reduction. And you can see that in some instances, the risk reductions almost come down to zero. And so we're explaining, in fact, less than zero here. We're explaining now pretty much the other 50% of treatment effect, nearly finished. And there's, if we reorder these, just to highlight, there's this series of phosphatidylinositol species. So in summary then, we've got LDL cholesterol lowering, at least in this analysis, explains about 50% of the statin treatment effect. The plasma lipids can explain the rest of that treatment effect. Reductions of particularly this phosphatidylinositol appear to be beneficial, and this may reflect statin action on either insulin resistance oxidation or oxidative stress or inflammation, as we've, in a number of other studies we've identified that these phosphatidylinositol species are tightly associated with insulin resistance and type 2 diabetes. So these may represent useful biomarkers and potential therapeutic targets in the future. Now, just in 1 minute, of course, this is all a bit esoteric. How does this relate to biomarkers and clinical use of these biomarkers? This has just come out in the last couple of weeks. Zora is a lipidomic biomarker company, and in fact we're working with Zora, so this is also my disclosures. But Zora had developed their own biomarker, which is a ratio of ceramide species. They've put this through a number of the same types of studies, and they're now partnering this with the Mayo Clinic to start to trial this in the clinic. And so that's really what this sort of test would look like. I think you need to get it down to a very simple single lipid, or at least a lipid ratio, a small group of lipids. And this is from the Mayo Clinic website. So I'll stop there. Just acknowledge many people have been involved in this, particularly John Symes and the group at CTC in Sydney. I'll stop there.
Thanks very much.